昨天彩排的时候，在这里拍了一张舞台的照片，然后发在了那个微信上面。然后有人说，哎，不明真相群众说，这是中国好声音吗？我说，这个差不多。不过呢，今天我们不是唱歌，我们是来讲故事。然后我今天要讲的故事呢，是跟材料相关的故事，是跟具体来说是可编程材料。然后因为呢，大部分的这些研究的话呢，我是在MIT 的时候做的，所以希望大家能够包涵我整个的这个演讲会用英文进行。So, okay, let's get started. So when I was studying in Germany, studying design, and there was this constantly debate in academic about this technology, which is the touch screen. So people are talking about how the technology is actually jeopardizing the design because everything we know, everything we experience about the world is now compressed in a very thin, flat material. In this case, it's the glass. And now what you need to do is actually just touch or swipe. And then this is frustrating because we as a human being, we live in a three-dimensional world, and then we love 2D more than we love 3D more than 2D, and then we want to make change about it. And then the more I start to think about it, and the more I found it's actually very interesting that actually if you look into our living situation, our living environment around that, the whole world is actually already constructed by flat and sheets material. So the fabric we're using is actually sewed into the clothes and also the curtains we're using. And the wood board is actually cutted and also screwed into cabinets and tables. And of course, the metal sheets we're using is actually compressed into the lampshade or whatever actually objects that we're using. So actually, the world is actually already constructed with a flat material. And then the difference is that the glass screen that we're using every day through our iPhone is magical, and then the normal material we're actually having around the world is not. So that's the ambition that I have when I enter the MIT Media Lab and in the Tangible Media Group. So actually, by the way, this is a place that we actually consider is the Hogwarts of Harry Potter in the real world, where actually people are really making magic. So I think for me, it's like what's interesting thing is how can we bring the magic that actually happens on your phone, on your tablet, to the normal materials that we're using every day, like your clothes, like your shoes, and also like your chairs, stuff like that. So I started making different experiments. I started looking at how can we create flat, thin material that can sense human stretch by embedding optical sensor in it. I started to think about how can you inflate thin membranes that create a dynamic, changeable surface texture that give you haptic feedback when you touch it. And also, of course, started to design this flat material that can transform into different shapes as you design it. Yeah, so, and then one thing actually echoes to the previous speaker that to 3D print a mechanical metamaterial that basically exhibits a unique behavior. In this case, when you compress it, instead of expand on the two sides, the material actually contrasts in the middle. So then I keep thinking about beyond the transformation and beyond the shapes that we can actually program in the material, what else we can do. This is a very interesting a picture I found online, which is describing the process of pottery making. That the pottery making is very interesting is that the material property, in this case, is stiffness, is constantly changing when the humidity changes. When it's wet, the whole material is actually fluid, it's malleable, and then when the humidity is low, and then the whole material becomes stiff, and then you can actually use it. So I start to ask myself this question, can we have a thin material that can show the similar property? Can we have a material that can be both as soft as skin and also as hard as a shell? And most importantly, can they just quickly oscillate and change in between these two stages? And since we're at MIT, the answer is of course yes. So basically, what we're looking at in this video now is that we develop a technology which is called layer jamming. It's looking at we basically composite layers of a thin material in this, for example, like a paper, sketch paper you guys are using, and then we place it into the airbag, and then when you basically vacuuming it, the whole material will become stiff. And actually today I brought a sample here, and I would like to show you guys how it works. So basically what you're going to see here is that it's a material that basically is flexible. And as I basically, when I turn down and then it's basically, yeah, you can make it into different shape. And then when I turn on the switch, the material becomes stiff. And then, of course, you can place something heavier in it, like, for example, like a water or something like that. And of course, once you switch it off, the whole material will become soft again. And then you can have it. So, yeah, back to the softer stage. So that's just a quick demo. And then you guys might probably wondering, like, actually, how does it work? What's the magic trick behind it? So actually, this is a little interactive session. If you guys can take out all your 如果你们把你们的那个门票拿出来，随便拿2-3张门票，然后当你们把你们的门票拿在手上的时候，然后如果你想要把它弯起来的时候，你会发现这门票就是这每2张纸之间，它们会有一些错位。这个时候，如果你开始对它上面的压力越压越大，越压越大的时候呢，然后这个错位就会变得越来越难。So in this case, this pressure is actually coming from atmosphere, which so basically means that when you're vacuuming it, you actually increase the friction between the layers. And then, of course, the more layer you have, the bigger friction you can get. And then the bigger the layer is, the bigger force you can get. And then we actually run through a mechanical test. In this case, we built this kind of test platform where we can basically testing between the soft and the stage and how much it changes. And then you can see that the torque changes between soft and stage is about like 44 times. And then this is just like a normal, simple sketch paper. And then, of course, we start to run through different thin sheets material like leather or fabric, paper, and sandpaper, something like that. And then so that basically we actually can analyze based on the material's properties, such as like the weight and the thickness, we can actually apply those material in different applications. So of course, since we were talking about screen before, and then of course the first application we can think about is like, today we're talking about the soft screen and a hard screen, but what if we can have a screen that can change between soft and hard? So in this case, you can see that when the display is showing leather, it's soft, and then we start to show the foam, it becomes relatively rigid, and you can sort of fold into different shape, but it still can hold the shape. And then when you start to display wood, and it becomes super rigid, and if you knock on it, you generate a sound of like a wood. So you can imagine that basically in the future, when you look at the material, you're only not looking at it, but you can also feel in it. And what about like, how can you change the stiffness based on the content of the movie you're displaying? In this case, is when it's displaying ice, it's stiff, and when it's displaying water, and it becomes soft. And then we start to think about how can we scale this technology up. This is the first time I actually built something that's bigger than me. And then so we're looking at how can we create a piece of furniture that can change from the carpet to a, let's say, a chair or something like that. So you can see that we can carry this soft and flexible and lightweight material around, and then basically we can form into the shape of the chair or a table, and then we actually can sit on it. And then after that, you become soft. And then you can use that to create a different type of chairs or lounge or even bed or bench to accommodate different usage in the interior scenario. What about medical devices? So in this case, we're looking at how can we create a arm cast that basically can comply to your human body when it's soft, and then we become rigid, you can actually protect your body. Say if you broke your bone, actually with this material, you can basically hold your arm, and then once it starts to recover, rehabilitate, and then the material becomes relatively soft, and then you can start to move your arm around. And then the interesting thing is when we're actually working on this application, it's exactly the time when the movie Big Hero 6 coming. How many people see that? 那个超能陆战队大白，有多少人看过那电影？ Anyway, so the idea is that when we start to thinking about like, so in the movie you see that this gigantic, very cute pneumatic robot that is soft, and then so because it's soft, it's like basically you want to hug it, you want to squish it, and then when it's in the emergent situation, it becomes and then all the armors like coming out on his body and then become a battle weapon. So we start to think about how can we create a robot that can change from the soft to hard. So in this case, we actually create a little inchworm that basically can move around. So you can think about this robot can basically go across different terrain and then to go into the different places. And then when it's reached to the specific position, and then you become rigid, so you can start to perform heavy duty and take loads, etc. And then after that, we start to think about how can we actually bring this material more close to our body. So in this case, we're looking at imagining how can we reinventing the shoe of the future of the shoes. So the idea behind it is that when we're running and we're walking, actually we have a different requirement of the shoes. Sometimes we want it to soft when we are walking. Sometimes we want it to be rigid when we're running to give a better protection of your ankle. So in this case, we embed the sensor in the insole of the shoe, and then it can detect the speed of the runner. So when you start to run, and then the upper part becomes rigid, lower part becomes soft, and then when you start to walk, it becomes another situation. And you probably start wondering, okay, you just showed me a prototype. That's not a real shoe. I'm not going to wear that on the street. So we actually went to a New Balance. Actually, they actually have a factory that is very close to Cambridge. And then so we went there and then started to collaborate with their shoe designers and shoemakers, and to actually using their machine to design a new type of shoe. And then this is actually the first prototype we designed is a shoelace-free shoe that basically can change from the soft to stiff to basically can hold the shoe on your feet. And something more experimental we are looking at is like to think about how the sheets material in the future can be the stiffness can be addressed. So in this case, we can see that we have this stiffness changing material, and then we weave them into a bigger sheets of material. And then you can individually control at a different area which part is stiff, which part is rigid. And why is it interesting? Because then you can actually create a material that you can only fold into one direction, and you cannot fold into another direction. And then you can really think about this can be used in the future, for example, in your clothes. And then your cloth itself can tell you how you should fold it by changing its stiffness. I want to go back to the design a little bit. How many people know this chair? Okay, so this is a classic design. During the World War II, this is from Eames Studio. So Eames actually, they developed a new process, a fabrication process called mold plywood to actually create, so basically this fabrication process to actually making people to be able to mold the wood into different shape. And I think this is a classic example of not the new fabrication process, a new material, not only create this kind of classical design, but also create a real product that impact the industry and the manufacturer. So we can really think about, with this stiffness changing material, how can we redesign and create a world that we actually live in. And then if we think about the application across the scale, I've already showed you that we can have something that basically you can wear on your body, like your clothes, your shoes. We can have something in the interior, like a domestic scale, like the chairs or the display you're using that can change the stiffness. And what about in the environment? Like, what about if we can go a little bit bigger, go a little bit broader? Can we actually have a car? The skin of the car can change the stiffness, so you actually give the user different emotions. Sometimes it's rigid. It's like, oh, this guy is tough. Some is soft. It's more like close to your body. And then can we actually use this material in the sailing boat to actually increase the safety of the sailor, and also possibly to let the sailor have a better control of the speed and the direction of when you are sailing. And if we want, we can go actually more broad and then more bold, is to think about how can we use this material to construct the future of the aircraft. So this is the picture of the NASA. They basically trying to make a shape-changing morphing wings. And then so can we have the material that change from softest to stiff, so it actually can better help the wings to shift its shape. I want to end my talk with a quote from my beloved advisor, Hiroshi Ishii. And then, so basically this quote can translate like this. 海洋与陆地相接的地方，生命在水、沙还有风的漩涡里变得多样。 今天我们站在一个原子与比特相接的海岸线上，试图平衡我们物理世界与数字世界之间的身份。So I think this is very interesting because today we are basically today we saw a lot of efforts has been made to negotiate this relationship between physical and digital. We design devices, gadgets, and systems to let people, and those systems can be programmed and reprogrammed so that people can enter this system and then to explore what's the digital world looking like. But I believe the next generation of programming should be something more material-based. Like the concept of the programming should totally coming out from the computer and enter to the physical material we're actually using. So what if those materials, their shape, property, and the behavior can be dynamically and computationally controlled and changed? So can we imagine a world that might be something like this? It could be something like this, and possibly something like this. So with all of that, I would like to first acknowledge all my collaborators on this project, and thanks for your attention.